Well, good evening and thanks for coming to Space Place tonight on the second Tuesday. It's our guest speaker night, of course, and tonight I would like to introduce our speaker, Evan Linck. Evan is a fifth-year graduate student in the astronomy department here at UW-Madison. He came to Madison after a background in public policy in Washington, D.C., so kind of a different background for astronomers here, and of course, potentially a good background should he go back to that at some point, then to have the science background that he now has. So tonight, Evan is going to talk to us about some of the work that he's been doing on piecing together the lives of the stars. So thank you for being here tonight, Evan.
Yeah, thank you very much. So good evening. Once again, my name is Evan. I'm a fifth-year grad student, and I study stars. And tonight, I really wanted to focus on some of the things that I've found the most interesting along the way of learning how to study stars, and some of the really big questions. So on the screen right now is an image from the James Webb Space Telescope of the Carina Nebula. This is a nebula that's forming stars. You can see some stars embedded in the bubbles of the gas and dust, and these have been recently formed there. About 4.5 billion years ago, our sun was probably in a cloud very much like this. And the material that we see around us was in that same cloud. And while that's a pretty profound thing, the idea of astronomers talking about we're all made of star stuff, the thing I'm actually more interested in right now is that 4.5 billion years number. How do we know that, right? That's wild that we know 4.5 billion years ago, our sun was probably something like this. And so that's really what I want to focus on tonight, is how do we know the life cycle of stars? Stars live for millions or billions of years, far beyond human lifespans. We really don't see most of them change. The vast majority of them always look the same to us. And yet, we have a pretty good understanding of how these things live and how they die. So, unlike experimental sciences, astronomy is observational, right? We can't go and touch these things. We can't go and fly out and get a scoop of a star to see what it's made out of. So we really have to rely on what comes to us, and that's light. The only information that we have to work with is the light that hits our telescopes. This is the WIN telescope, the telescope that I use in southern Arizona for my research. The W in WIN stands for Wisconsin, so Wisconsin owns a percentage of this telescope, and it's a 3.5-meter telescope. Just wanted to show some pictures, and there's more information in the other room as well. So in this talk, I really want to explore three questions. Roughly, how do we measure things? What patterns emerge from the measurements we've made? And then how do some stars deviate from these patterns? So first, how do we study stars? Well, we look at the night sky. We can see things like constellations. You have Orion and Taurus, the Pleiades, and the Canis Major down there. You have some well-known stars. Betelgeuse is the reddish yellow star kind of to the middle left. You have Sirius down in the bottom left corner, that very bright star. Above the Pleiades, that bright star up there is Algol. And then you also have some stars that are somewhat clustered together. So what sorts of characteristics do you see about the stars here? How would you describe some of the differences that you're seeing?
Color difference.
Yeah, so color. Any other things? And brightness, yeah, color and brightness. And also with the Pleiades, some of them are grouped together with each other. But we can get a couple of characteristics of some hints about what's going on with stars just by looking up at the night sky. So when you actually leave tonight, look up, this is exactly what you'll see, are these clusters. They are all winter constellations. So the next thing we can do is study the sun. One of the big benefits is it's right there. It's really easy to see the small, that's in quotes for those online, details, where many of the small details are actually massive. We can see things like outbursts that follow magnetic field lines. We can see sunspots. These are cooler areas on the sun's surface. The big sunspot right there is about the size of the Earth in terms of scale. So small compared to the sun, pretty big compared to us. We also are able to study things like the solar wind. So there are particles that are being ejected from the sun, and they hit the Earth's atmosphere and create auroras. One big con of studying the sun is it's not representative of many of the stars that we can see in the night sky. But there are some other things that we can do using the sun, and that's study nuclear fusion. So one of the really big mysteries in early 20th century physics was we know that the sun produces a lot of energy. We go outside, we get a sunburn, like that energy has to come from somewhere. But how does the sun power itself? And so there are a couple of clues that finally got to the correct answer. The first is that the sun is 91% hydrogen. The element helium was first discovered in the sun, comes from helios, of the sun, comprises about 9% of the matter of the sun. And then finally, we start getting into the quantum mechanics side of things. Someone noticed that the mass of a hydrogen, or 4 hydrogen atoms, is slightly more massive than the mass of 1 helium atom. And that slightly different amount of mass is converted to energy through Einstein's equation, E equals mc squared, when fusion occurs, taking 4 hydrogen atoms and putting it into 1 helium atom. And so folks in the early 1920s really started to piece together that stars are powered through fusion in their core. They're taking hydrogen and fusing it to helium, and later on, helium is being fused into carbon, and so on and so forth, to heavier elements. But that's something that we can learn from the sun. So, we've learned a lot of things looking at the sun, but maybe we need to go elsewhere. We can start taking photos of nearby stars. These stars are still close enough that we might be able to see some details, and we now are starting to get a larger sample size where we're able to see stars in different stages of their life cycle. So for example, the first one, Proxima Centauri, is the next nearest star to the Earth after the sun. It's only about 1/8 of the mass of the sun. It's barely massive enough to actually be fusing hydrogen in its core. On the other hand, we see stars like Betelgeuse, and this is an actual picture of Betelgeuse, fully resolved. It's one of about 20 stars, aside from the sun, that we can see the full disk. It's not just a point source of light. This is a red supergiant, very close to the end of its life. We can see it's not fully spherical. It's somewhat blobby. It's not really able to fully control its outer extents anymore because it is just so large. And it long ago has stopped fusing hydrogen in its core. We also can see stars that have companions. So here are Mizar and Alcor. These are stars in the handle of the Big Dipper, right where the kink occurs. With a good pair of binoculars, you can see they're actually binary stars that are orbiting each other. These are stars that were born together and continue to be gravitationally bound, orbiting each other over time. We can also see stars that display a wide variety of physical processes. So I mentioned Sirius before. Sirius A, the very bright star, one of the brightest stars in the night sky, has a companion. That little dot to the side is Sirius B, and that's what's called a white dwarf star. It's the remnant core of a star that's died. The hot thermal emitter that's still just kind of ticking away. Can't see that with our naked eye, unfortunately. But one thing that's very interesting about stars like white dwarf stars are they're very heavy. So that star is about the size of the Earth, but it weighs the same amount as the sun does. And so we can see all of these exotic stars and stars in different stages of their life really close to us just by taking some photos. So as just kind of an overview, we'll talk about a couple of terms of some of the stars that we see nearby. So when we look at nearby stars, see a pretty wide variety of stars. There are dwarf stars like the sun, a yellow dwarf, red dwarf stars, which are slightly less massive. There are stars that are different colors. Hotter stars are bluer, cooler stars are redder. You can think of a candle flame, that the hottest part of the flame is the place right next to ignition. It's a blue color. When you get to the edges, things have cooled off a little bit. It's a redder color. Same thing applies to stars. But we also see a wide range in temperature of dwarf stars. They go all the way from very red to very blue stars. In general, giant stars are cool and also very big. The red giant and red supergiant are these massive red stars. But like a candle flame, their outer reaches are actually fairly cool in comparison to the outer reaches of a star like the sun, or especially Sirius A, as we were seeing earlier. I mentioned white dwarf stars, the remnant core of stars after they have died. There are also brown dwarf stars, and these are stars that never became quite massive enough to fuse helium. So they're fusing things like deuterium or lithium instead. And these can last for many, many billions of years, just slowly chugging away on the tiny amount of deuterium that they have. So we've now taken some photos of nearby stars. But what if we start taking photos of the same star many times in a row? we can start to piece together some pretty interesting characteristics. So what we're looking at here is Algol. I pointed out on the night sky. And Algol is an eclipsing binary star. So this is actually one of the other stars that we have resolved. You can see the main star in the center, Algol, and another star that is orbiting it and passing behind the disk and now in front of the disk. And if we take many photos of a star in a row, we can start to discover some characteristics about the system. So if we take all of the light that's in the image and sum it up at a single point in time, and then start graphing it over time, at first we'll see that when both stars are fully visible, we get the largest amount of light that we're going to get. And then as one star passes behind the other, the total amount of light we have dips. And it goes back up and kind of levels out, and then we get another smaller dip when the less bright star goes in front of, eclipses the brighter star. So we call this image on the right-hand side a light curve, and we can study many things using light curves. I also want to point out that Algol is a famous early eclipsing binary, and that one of the early directors of Washburn Observatory, Joel Stebbins, actually was the one who first made the light curve using an electronic device. So it's just some fun Wisconsin history going into this famous binary star. So light curves really can show many different characteristics, many signals that come from stars, from their fluctuations in light over time. We can see things like rotation. So say there's a star spot, like a sunspot on the sun, but it's another star, so a star spot that is slowly going across the face of the star as it rotates. We can see the light from the star will go up and down as this cooler part passes in front of it and then behind it. We can also see things like flares. The spiky bits of the light curve are flares that are coming off of the surface of the star. We can see things like pulsations, where the star grows bigger and smaller. As it gets bigger, it gets brighter. As it grows smaller, it gets dimmer. And as we saw before, we can also see eclipses. So now we have taken photos of specific stars. We've taken many photos of those stars over time. But what if we start taking photos that are a bit wider field, where we're getting them in the context, the environment that they live in? Who are their neighbors? At the beginning of the talk, we saw the Carina Nebula. Here is the famous Horsehead Nebula, and you can see a very bright blue star that's clustered in this bubble of gas that it formed out of. Maybe a little bit later, we might see something that's called an open cluster. These are stars that were all born together. They're formed out of the same cloud of gas and dust, and they live their lives gravitationally bound to one another. And even further down the line, maybe we see globular clusters. Globular clusters are millions of stars, or a million-ish stars or so, that were all born out of the same very large cloud of gas and dust, and continue to be gravitationally bound over billions of years. So, now taking a wide field photo. What if we start taking wide field photos over the course of a year? Well, if we were to take a photo of, say, a star that's not too far away today, and we take another photo of it in August, what would end up happening is we would see the star shift its angle in comparison to the stars in the background. And this is called parallax. So we're going to do an audience demo really quick where we're going to do parallax. So one thing that I'll have everyone, you want to do that? Okay, great. So for everyone in the audience, we'll do a quick demo of parallax. So if everyone wants to put a finger up and close one eye, and then have your finger placed over some distant object that you can cover up. Now close your open eye and open the other one. And you'll notice that the angle of your finger changed compared to the background thing that you're covering up. You're now covering up a different object. That's the effect that's called parallax. And with a little bit of trigonometry and knowing what the distance between our two different pictures were, for us it's our eyes. For something like parallax in astronomy, it's the orbit of the Earth on one side of its orbit, and then 6 months later on the other side of its orbit. You can actually see the foreground stars shift back and forth, somewhat like in that demo on the right, or the image on the right-hand side, which is an exaggerated version of parallax. But with a little trigonometry, we can now start measuring the distances to these objects. It's just a few angles that you have to compute, and if you know the distances between your eyes or between the Earth at different parts of its orbit, you suddenly start to understand how far away these stars are. So, now let's take a wide field photo over many years. And we can actually see that some stars start to move in the plane of the sky. We call this proper motion. So this is the speed or the velocity that a star is moving compared to other stars in the background over many years of time. So this is an image of Barnard's star. These images were taken 50 years apart from each other. This star also has the highest proper motion, 10 arc seconds per year. And so to give some reference frame for what an arc second is, if you have a circle, has 360 degrees in it, every degree has 60 arc minutes, and every arc minute has 60 arc seconds. So it's moving quite fast compared to other stars. You might also see a few other stars, such as just in the middle and to the left a little bit, there's another star that moves down a little bit between the two. And most stars show movement like that or smaller, measured in milli-arc seconds per year. And as a frame of reference, 1 arc second is if you took a dime and you looked at the angle made between both sides of the dime and moved the dime 2.5 miles away, that's 1 arc second. So a milli-arc second is the angle made by the two sides of a dime if it were in Panama and you were here and you're able to see it. And we're able to start to measure that now. So what we've been talking about so far are fields called photometry and astrometry. So photometry, it's about the brightnesses, the colors. Astrometry, it's about the positions and the motions of stars. So just wanted to give a kind of current state of the field, where we are today. The images we've been looking at have been more historical images. So on the left-hand side, you can see an artist's rendition of the Gaia satellite. And this satellite was launched in 2013 and has been taking pictures of the whole night sky every day since then, and slowly tracking the positions of stars over that time. And so I have up here on the other side an image of an artist's rendition of the Milky Way, our galaxy. And when I say that Gaia has been revolutionary in terms of the science it's allowed us to do, I really mean it. It now covers about 1/3 of our galaxy. So the photographic plates that we saw earlier of Barnard's star were really only looking at stars that were right next to the Earth. We now can see stars that are on the other side of our galaxy using Gaia. So the latest data release in Gaia has 1.5 billion stars that have proper motion and parallax and color, and 1.8 billion stars that have a brightness measurement that's associated with it. So this is what we can start to do when we take wide field photos over many years, is we can start to get information on all of the stars that we can see out to 1/3 of the galaxy. So we've talked about how light can be used in photometry and astrometry, but there's another dimension that we can use light. It's called spectroscopy. So instead of taking a photo of all of the light that comes in from the detector, what if we put a prism in the way first and broke the light out into its constituent parts, where we see all of the wavelengths of the light that are coming in? So one thing that is very fortunate for us as astronomers is that every element has its own signature in spectral lines that correspond to the wavelengths that it emits at and absorbs at. So on the right-hand side, you can see the spectral lines of several atoms. Up top is hydrogen, then helium, mercury, and uranium. And you'll notice that every single one of these has very distinct lines where it is emitting. It turns out that if light of that wavelength were to pass by this atom, it would also absorb at that specific wavelength, so kind of a black bar instead of a bright colored bar there. We also have continuous light, so the full rainbow at once, and this is created by thermal emitters, or things that are hot that are emitting things, that are emitting light because they are hot. And if that sounds familiar, it's because it's a star. Stars are hot things that are emitting thermal emissions. And so one thing that is very useful from what we know about spectroscopy and different chemical elements from studies here on Earth is that we can actually start to see the atoms in a star's atmosphere absorb some of that light. So if you look at the rainbow bars that are spanning across, you can see these black bands that are coming down and blocking out or taking some of the light away. And those are the exact same bands as hydrogen up here. So we can see that it's a hydrogen-rich atmosphere. There's some hydrogen in the way of the star's thermal emission that's being absorbed by the energy, or by the atoms that are in the outer atmosphere. But it's not just hydrogen. It turns out that Every element has its own unique spectral signal. And so if we can look at the absorption features from different atoms and look at their ratios, we can actually figure out what the chemical composition is of stars far away, because we can see the different ratios of different types of matter that are absorbing light in the upper atmosphere. So now we can start to put some pieces together and see how some patterns are emerging. So stars have different absorption features that are based on temperature. On the right-hand side, you can see some spectral observations of different stars, with the hottest stars up top going down to the coolest stars on the bottom. And you'll see that there are different features for, let's see, where else? You can see that there are some different features, that you have these thick, deep bands right here, but they somewhat disappear. In the coolest stars, there are a lot of molecular lines along the bottom. You'll also notice that the hottest stars are producing more blue light. They're both hotter, they're giving off more intense light, and they're producing bluer light. So now we can start to realize that when we are looking at stars, as we've talked about with the candle, color of a star can be used as a proxy for temperature, and that backs up with our spectral observations. So there's one more property that we can use with stellar spectra. So like with wide field observations, where we start taking them over the course of a year or many years, what if we start taking spectral observations over the course of a year or many years? And it turns out this can actually give us a property called radial velocity. So radial velocity is motion along the line of sight. So when you talk about proper motion, that's in the plane of the sky compared to the other stars. It's an angle. Radial velocity is the velocity that something is moving towards you or away from you. So if you imagine an ambulance that is coming from behind you and going past you, the frequency of the sound goes up and then goes down. That's called the Doppler shift, or a Doppler effect. Turns out that light does the exact same thing. It also has frequencies involved. And so if something is moving towards you or away from you, it will actually start to shift the spectra back and forth. And binary stars do that. As a star orbits towards you, as it gets closer towards you, you'll get a shift in one direction. As it starts to move away from you, you get a shift in another direction. So in the center, you can see a binary star orbiting another star. And on the top right, you can see the speed over time. And then the bottom right, you can see its spectrum moving back and forth. And so if we get enough observations like this, if we know the velocity of the star at different times, we can actually reconstruct the orbit of the star. And that's actually really important in astronomy. It turns out that orbits are really the only way to get accurate masses for things. So the orbital equations are based on how much stuff there is, how much mass the two bodies have as they orbit each other. And very few other properties are based on that. And so this is a direct way to actually measure the amount of stuff where we couldn't measure it in any other way. It's a property that we want to know. How much stuff happens to be in this region? And the only way to really figure it out is to find an orbit and do something along the lines of Doppler shifts to figure out how much matter there is. So then, summary of observable properties in stars. We have a brightness, we have a color, temperature. We see variations in the light curve due to pulsations, rotation, flares. We can also measure the distance through parallax. We can measure position relative to other stars. We know the chemical composition of stars from spectra. We can see variations in spectral observation, which help us deduce the motion of the stars, and we can get three-dimensional motion. And finally, we can figure out things like binarity and mass. So that's a lot of information that's contained in the light. But we really need to have some additional context to figure out what all of this means. So we can do things like laboratory experiments. This is the big red ball on the right-hand side. It's a fusion experiment that goes on in the basement of the building that I work in, so I get to see this through a little window every day when I walk to work. But it's studying how fusion occurs in astrophysical environments. We can also look in the laboratory for spectral signals of different molecules, of atoms, do atomic physics. Chemistry in extreme environments is really important. Maybe something occurs in a vacuum or only at 1,000,000 degrees. We can do these sorts of experiments in laboratories. There are also properties of subatomic particles that we might care about, like neutrinos. Those we can do here on Earth. And finally, things like thermodynamics and fluid mechanics. So, I know showing math in a talk is bad, but it's not that bad. I'm not going to go through it. But we can use theoretical physics also to understand stars. Turns out that stars are driven by processes that are the same as processes here on Earth. Things like gravity, fluid mechanics, thermodynamics, quantum mechanics. It's just at the far extremes of all of these things. And one thing that is very beneficial in stars is that we can apply the same laws that we have because of that. So on the right-hand side, you see the four equations of stellar structure. The entire life cycle of a star is based on these four equations. It's actually pretty small amounts of things that go into saying how a star will change over its life cycle. And it's four equations that will govern the entire thing. But what's really important about just having four equations like this is we can make numerical models. Whenever you have some sort of analytical equation, you can ask a computer to run it again and again and again forever. You don't have to sit down by hand doing out the math, because I can tell you, I do not like doing the math on the far side, but I don't mind if my computer does it. So we can run simplified analytical models on a laptop. We can also do detailed three-dimensional numerical models that run on supercomputers. So on the right-hand side here, you can actually see some simulations of the structure of neutron stars. These are very dense stars composed of just neutrons. And this is not something we could go out and touch, go out and see, go out and probe to the center, and yet we have a really good idea of its structure because it follows the same laws of physics here on Earth, and we can model it to understand how that works. So, whirlwind tour of all of the different ways that we can get information from light. So let's go to the next question. What patterns emerge from our measurements? And I want to talk about this in the context of clusters, as I think it's kind of an easier way to introduce this subject. So as I had mentioned earlier, a cluster of stars forms from the same cloud of gas and dust. The thing that is fundamentally important about working with these environments is that we get to make a couple of generalities about the stars that we see. The first big one is the stars are all the same age. They all formed out of the same cloud of gas and dust at more or less the same time, give or take a few million years, which on the lifespan of stars, that's essentially the same time. They're also made out of the same cloud, so they should have more or less the same chemical composition as each other. But the thing that's different, which is important, is that every star will have its own mass. Just some random amount of gas and dust collapsed into a star. So there'll be a wide range of masses in the population of stars. So one thing we can do to start looking at patterns is maybe we could sort all of the stars in a cluster by color and brightness. So here's just a movie doing that. So this is a very zoomed in picture of a globular cluster, again, million stars or so. And the European Space Agency put together this video. So they first sort all of the stars by color. The bluest, hottest stars on the left, the coolest, reddest stars on the right. We can then start to sort them by brightness. Brighter stars up top, fainter stars at the bottom. And now we get a really distinct function. Yeah, it's one of the best videos that I've ever seen demonstrating this, that we can actually see all of the different stages of stellar evolution in a single diagram. We have a nice, smooth curve, and we'll walk through what all of this means. So what we have rediscovered is what we call the Hertzsprung-Russell diagram. So before I go through each of the individual parts, there's just a couple of things that I want to remind you of that we've talked about. So stars like our sun burn hydrogen in their cores. Stars that are more massive are hotter. They burn through their fuel quicker than stars that are lower mass. So therefore they become giant stars earlier and they die faster than lower mass stars. And importantly, all of the stars in the cluster are the same age as each other. So the pattern that we see has to be a function of mass only. Just the amount of stuff the star started with determines its position on this diagram at a given time. And we can measure these masses if we can find those stars in binary orbits. And turns out binaries are pretty common. So we can measure masses of many different stars at different parts of this diagram. So what we have now, what we've built to, is a map of the different stages of stellar evolution. The position on this diagram is really just based on the energy source that's at the center of the star. So we'll walk through these and talk about the different properties that we see. So the big line that's from the middle of the image all the way to the bottom right corner is what we call the main sequence. All of the dwarf stars live on the main sequence. The sun is currently on its main sequence. These stars are all burning hydrogen in their core. But as more massive stars run through their fuel quicker and run out of hydrogen, they turn off the main sequence and they start going up the red giant branch until they get to the very tip of it, where the center of the star, the core of it, gets hot enough that helium fusion begins, and it starts to burn helium in its core. And eventually it might burn carbon and oxygen, and if it's massive enough, into things like neon and silicon, all the way up to iron. The star then turns into what's called an asymptotic giant branch star, an AGB star. And when it's in this phase, it starts to lose most of its mass through winds. And as the star loses more mass and loses more mass, it gets to just the core of the star, which is what we call a white dwarf star. And at this point, it's no longer burning anything in its core. A quantum mechanics effect is actually supporting the star by itself. So it's just slowly radiating away heat, a very blue, hot object that cools down over the course of several billion years. But so now we've gotten to the basics of stellar evolution in a single population. So much like before, where we went from a single image to looking at images over time, what if we start looking at different clusters together? So when we look at different clusters, what we end up seeing is that not all of the stars line up with each other. So on the diagram to the right, there are two open clusters, M67 and NGC 188, and their stars are plotted on an HR diagram. And you'll notice that the main sequence, the lower part of it, lines up quite well. The blue stars overlap the yellow stars. But if you look near the turnoff, M67 has stars that are brighter and bluer than the stars of the turnoff of NGC 188. So we know that stars that are brighter and bluer are more massive, and that massive stars have a shorter lifespan. Therefore, the massive stars in NGC 188 have already died. That's why they're missing, is because they have gone through their entire life cycle by this point. And so really what that means is that NGC 188 must be older than M67 by a decent amount, that it no longer has some of the same stars. And likewise, some of the stars in M67 that are a little bit further down the main sequence, at the age of NGC 188, would become the giant population in that cluster. So what we're really able to do is clusters let us see stellar populations of different ages. And so now we have a time component to how these stars evolve over time. So we can get to building models. So in astronomy, we have a model that we use a lot called an isochrone. Iso for same, chrone for time. And it's really looking at where stars of different masses would be at a certain time during their evolution. So we can construct these models of stellar evolution, and we can fit them to our observations of clusters. And what we see is a map that maps out younger clusters and how they change as they become older and older and older through time. And so it really maps the age of populations and the characteristics of stellar populations at certain times. So as kind of a reminder, we started this talk talking about observing points of light in the sky, their color and their brightness, maybe we know a distance or something like that. But we've now been able to build up to how stars of different masses and compositions change over time. And so we have this map. So maybe we could take the map and apply it the other direction and do statistics where if we observe certain characteristics of a star that's not in a cluster, maybe we can determine its age based off of stars that were in clusters. So we'll get back to Gaia and what we currently understand about stellar evolution. So on the right-hand side are the map of 1.5 billion stars and where they are in their current set of evolution. And the way that we understand their life cycles is we observe some of their stellar properties, color, brightness, the mass from binaries. We can then model the physics of the star. How fast would a star of a given mass use its fuel? we can start then examining stars in clusters, and through some inferences about ages of the populations, we can look at how clusters change over time. And then finally, we can take the information we've learned and start to do statistics on 1.5 billion stars. And that's how we know that the sun is about 4.5 billion years old, is because we've found other stars like the sun elsewhere. And we know their ages through this process. So, this is our idea of single star evolution. But it turns out there's some things that deviate from this. So now I want to talk a little bit about some of the research that I do about stars that deviate from stellar evolution patterns that we observe everywhere else. So I'm going to talk a little bit about a population that are called blue straggler stars. So real clusters have stars that do not lie on their isochrone. The most well-studied of these are the blue straggler stars. These stars are bluer and brighter than stars that are just running out of hydrogen in their cores, so at the turnoff. So these stars appear to be too massive to have survived at the host cluster's age. So stars that are brighter and bluer should have gone through their mass, or should have burned through their fuel much quicker, and yet we see them. And because clusters stars are all the same age, it means that something has happened to these stars over time. So all of the, all the stars in the cluster are the same age. So really what so the question is, why do we see these stars that appear to be so massive that they should have died long ago? And the theory is they have gained mass after formation. And the way that we know this is most of the blue straggler stars are in binary stars. And binary stars can interact with one another. So on the right-hand side, we can see some different diagrams of how these stars will interact. First, they can collide with one another, just smack head-on, release some mass out into space, and merge into a single star. They can also merge with each other, which is a slower process, a much gentler process, and end up with much more mass instead of a big collision. They can also undergo mass transfer, where the outer layers of a star, as it turns into a giant and gets much bigger, are more gravitationally attracted to the companion star and get ripped off one star and dumped onto the other. And each of these different interactions will increase the mass of the star well after it's born, maybe billions of years later. And ultimately, the orbital period of the star determines if and when a star will interact. Now, these interactions are all very quick. They're hard to observe. They're things that maybe if we get very, very lucky, we'll see one of these. But we know that these things exist because we see stars that have demonstrated they've gone through some sort of increase in mass. So we can turn to models. And so I'm going to play a short demo or a short movie of a star undergoing mass transfer. So as a star turns into a red giant, its outer layers can become more gravitationally attracted to the companion star and get ripped off. And this will go all the way down until the original star has just its exposed core, which is a white dwarf star. The other star will then accrete the material, becoming more massive, brighter and bluer. And so this is how we expect mass transfer to occur in many cases.
Density difference, if you mind if I ask, the white
Yeah.
dwarf, you said its weight, its density is much greater. What is that? Is that an elemental issue? What's
Yeah, so that's a great question. So the question is, why are white dwarfs so dense? What causes that to be? So it's actually being supported by quantum mechanics, or a quantum mechanic effect called the Pauli exclusion principle. So for stars like the giant star or the main sequence star we see beforehand, it's being supported by energy that's coming from fusion. So hydrogen atoms colliding, forming helium, little extra energy is coming off. When you run out of all of that, you get to a point where there's no more material that's really there's no more energy that's really going outwards being created through fusion. And so stars, material will start to condense into denser and denser forms. And so when you get to very extreme densities, there are certain quantum mechanics effects that will occur. So If you think back to the spectral lines that we saw a little while ago, each one of those spectral lines really demonstrates or shows one of the energy levels that an atom can be at. So if you remember all the way back to high school chemistry and you have different orbital levels, each one of these has a distinct state. And it turns out when you fill up a state, you can't put anything else into that state. It's full, doesn't accept anything else. In a white dwarf star, there are only so many states that the electrons can be in. Once you get to the maximum number, you cannot add anything else. And that essentially creates a pressure, which is pushing outwards. As the white dwarf is trying to become more and more dense, it can't add more electrons to that area. And so it supports itself through this quantum mechanics effect. And it just keeps cooling down until it becomes effectively a diamond or something like that, a crystalline structure. Yeah, of course. So we've seen some models of these stars, but I wanted to talk very briefly about the state of research on this. So some insight into the blue straggler formation mechanisms. So these are collisions, they're mergers, mass transfer. So the current state of research is really trying to ask questions like, what is the frequency of each of these formation mechanisms? Are things like mass transfer more frequent than collisions or mergers? Does it depend on the density of the environment, the distribution of periods in binary stars? Another one is, how long ago did a star form as a blue straggler star? We know it wasn't born as a blue straggler star. It had to have gained mass later, otherwise it would have died a long time ago. So how long ago did these things form? What's the rate that they form in different sorts of environments? As I mentioned, it's also very hard to observe these things, but we can observe them after they've occurred, and we can observe systems that are progenitors that are before they have interacted. And so can we make maps from one side to another to constrain the physics that's actually occurring here? We can use things like orbital characteristics, the periods we observe, stellar rotation and pulsation. We can use the temperature of a white dwarf as it cools off over time. That actually creates essentially a mapping to how long ago it occurred, because white dwarfs will cool off at certain rates over time. And really, the ultimate question that we're trying to ask is, can we learn the story of binary evolution like we did with single stars? We saw that map of 1.5 billion stars from Gaia. Can we do a similar thing with how all of the ways binary stars will interact and the different ways they'll deviate from the picture that we saw earlier? So with that, I want to say thank you and leave a picture of the Cat's Eye Nebula, which is a dead binary star.
Thank you, Evan. I think I'll leave the recording running just for a moment, because we're not short on time here.
Yeah.
I think. Anybody got any questions? Yeah, go ahead.
One of your slides, you had I think it was the graph of the light graph, and you had an orbiting,
Yeah.
on the corner, the lower left-hand corner, you had orbiting,
So
there.
this one.
What are those digits, the scrolling digits?
Yeah.
What does that signify?
So
Sort of repeat the question.
yeah, so for the folks online, the question was, there are some digits that are in the bottom left-hand corner of this image of Algol orbiting itself. What does that mean? And this is actually the phase of the orbit. So the orbit itself is about 2.8 days. So we can see these big dips every 2.8 days. And so the phase is what percentage of the orbit is it in? And so this number goes from 0 to 1, with 1 being the end of the phase, and it wraps around to 0 at that point.
So there's units, I mean, a unit is a percentage.
Yeah, percentage of the total time it takes to orbit.
Thank you. I just was.
Yeah, of course.
So different binaries would have different orbital periods, and that's just.
But yeah, but then we'd have the same use of phase, because then it's a kind of a way to put them all on the same scale as each other, so you can see different properties of them in relative order.
I'm a little, my comment here is I'm been surprised 2 days for these massive objects
Yeah.
orbit each other. That's
Mm-hmm.
that seems to be substantial amount of gravity to be able to
Yeah.
make it rotate that.
Yeah. So 2 days is a very fast orbit, but we actually know stars that are 2 hours apart from each other. So it turns out that stars that are that close to each other are likely interacting with one another. These stars, at some point in the future, as the main star runs out of hydrogen in its core, it'll become a giant, and it will probably end up going through what's called a common envelope merger situation with the other star, where it will absorb the other star or push it to an extremely low period, something on order of hours. But most binary stars are significantly longer periods. So the only thing that really determines the period of the star is where it started when it was born. When the cloud of gas and dust was collapsing down into stars, what other stars were nearby and gravitationally bound to that same region. And so you can have things that go from a couple of hours all the way out to 100 million years. It just depends on what sort of environment it's in. At 100 million years, a light breeze, another star barely passing by might disrupt the orbit. But for something like this, these things are right next to each other, and it's going to be very hard to separate them. But so you can have this very wide range over 8 orders of magnitude, 9 orders of magnitude in periods of binaries. Yeah.
Cool. So this is an observational field of study, astronomy.
Yep.
You pointed out, and I think you did a wonderful job of the way you were measuring things, how you conveyed that in your presentation. I mean, sort of a laundry list of techniques. It was great. So looking at that, I mean, there's some cutting edge, the field of cutting edge astronomy. What are some other tools in the toolbox you see that, that aren't listed on you had a laundry list of, here we go, here's how we can measure and gain information.
Yeah.
But there must be some other ones that are, somewhere that you could add to this element of gathering data.
Yeah,
Is
so
that a fair question?
it's a great question. So the question was, so we've talked about many different ways that essentially you can take photos of things. What other ways do astronomers study these distant objects? And so we're now entering a phase of astronomy that's called multi-messenger astronomy. So instead of just light that's reaching our detectors, we also have things like neutrinos reaching our detectors, or gravitational waves that are reaching our detectors. And so we have some other signals that we're able to start observing. So this laundry list that we went through was really on the ways that we can exploit the properties of light to figure out what's going on. And that was most of astronomy, was we just had the light that reached us. But now we're able to start probing things that are really getting at more exotic features and phenomena. For example, merging black holes will create gravitational waves that we can measure in our detectors. And so we're starting to get more information.
That's awesome. Thank you. I don't mean, I said laundry list.
No, it's,
I mean that in some sort of
yeah.
sense. I just wanted
This was meant to be let's go from the start and let's just go through.
A slide that covered a whole facets of the tools, if you will, that you're using to get this information. So it's really great. I mean, for a casual observer to understand this.
Thanks. Yeah, Jim.
Yeah, so my question is, you showed the blue straggler formation. You showed a couple of scenarios of blue straggler formation, the stars interacting, and you said these happen really fast. So I presume you don't see any specific examples of these things interacting. It happens too fast for us to ever catch.
So it can really depend on the time scale. So a collision of stars is somewhat of a happenstance. Two stars are in a cluster environment, and usually they're in a binary of some sort, and another star comes along, and they swing around each other in such a way that they catch each other and collide. That happens more or less instantaneously. We don't see those ever. For things like mergers, same sort of deal. It's very hard. These processes occur quite quickly. The actual merger event itself, numerical models suggest it takes anywhere from about 300 days to about 4,000 days or so. So a couple of years at most. And that's from the point where the star starts to enter the upper atmosphere of the other star. And there's an event called the plunge, where friction pushes the other star into one of them.
Okay, but that description you're giving there is based on theoretical models.
Yeah, it's based on numerical models. Yes, it's based on numerical models.
The slower process.
And so then mass transfer can occur at lower rates, can occur over millions of years, but at rates that we'd really be able to notice occur over much shorter spans of time. And so there are a couple of systems that we know about that we suspect mass transfer is going on, where we see infrared radiation coming from gas and dust being thrown off. But it's really hard to measure. These are very weak signals. And so it's also really the domain still of numerical modeling. But what isn't the domain of numerical modeling is we can see these systems afterwards. We know, compared to clusters that they're in, that they've gained more mass. So we know something has to have happened to them. We see evidence that these things are around.
So the presence of the blue stragglers is the evidence for these interactions.
That something is, yeah.
But you suggested that, is there any indicator of how many of them have white dwarf companions? Something
Yeah.
over from
So
this
that's,
interaction?
so that's a great question. So the question essentially is, one of the end products of something like mass transfer is that you will be left with the remnant core of the star that gave away its mass, a white dwarf star. And how many of these do we actually see? And it turns out we see a decent number of them. So I was showing the cluster NGC 188 earlier. There are 21 blue stragglers in NGC 188. And we have measured temperatures of hot white dwarf stars for 7 of the 21 of these stars. For many of the others, we suspect they might have a white dwarf companion, but these stars have cooled off so much that we can't see them anymore with our detectors. But if we look at, so I was talking about how binary stars, you can measure the masses. If we look at what the distribution of possible secondary masses, the less massive companion star are, it is the exact same mass as a carbon-oxygen white dwarf star. So we suspect that whatever is orbiting it has the same mass as a white dwarf star. We can't see it, but it's probably a white dwarf.
Do you see the radial velocity?
We see the radial velocity in the blue straggler itself. And so we can make some very educated guesses as to what the mass of the companion is based off of its orbit. And it's the same mass as a white dwarf star. So we can use these sorts of other lines of evidence. So I'm actually working on this big project right now where we are taking about 2,000 stars that are in the field that we suspect have white dwarf companions. And we're seeing all sorts of unique systems, including stars where the white dwarf is more massive than the star that we can actually see that's big and bright. That there's more mass there, but it's so dim that it's just not really being picked up by our detectors. But its orbit is suggesting that the star is more massive than the star we can actually see giving off light. But it's so small, it's just not giving off that much.
Okay, well, thank you once again, Evan, for your talk, and I really appreciate the background here on all this tonight.
Yeah, well, thank you.